This is Algebra 2 with trig 2b.5a. We're going to factor polynomials. Now, when we're factoring, what we're going to pay attention to are some strategies. The first thing you always want to do is look for the greatest common factor. Greatest common factor. So, does your function have a greatest common factor that can be pulled out? Always want to look for that. Then we are going to try to notice the number of terms that we're working with. Do we have 4 terms? That's new for what we're doing today. If you have 4 terms, you're going to factor by grouping. If you have 3 terms, then that can be made by the product of 2 binomials. That's what we've done in the past. And then 2 terms, like the difference of 2 squares. That's what we've done in the past. We're going to learn the sum and difference of 2 cubes today. Alright? So this might be a good little strategy to look at to see what you might do. So when we're factoring, always look for a GCF. You always want to take that out first. And then we're going to continue on factoring until it cannot be factored any further. So here we are with our first one. This would be considered a trinomial because it's got 3 terms. This is a cubic. We've never factored a cubic before. But notice how there is a y in every term. So if there's a y in every term, I can pull that y out. So now I have 1 less y in each term. So that was my GCF. Now you got to consider, is this factorable? Is there something that multiplies to be 12 and adds to be negative 4? In your head, you would be thinking about a table, negative 12 and negative 4. What adds to be negative 4 and multiplies to be negative 12? You probably know it by now. You know your 2 signs have to be different to multiply to be negative 12. And your larger number has to be negative to add to be negative 4. What makes this a little tough is that there's multiple ways to get to 12. 1 in negative 12, 2 in negative 6, 3 in negative 4. There's several different ways. But one of those ways does add to negative 4. This one adds to negative 1, this one adds to negative 11, but this is the one that adds to negative 4. So we're going to use y plus 2, y positive 2, y negative 6, y minus 6. If you were to multiply that out, FOIL it together, and then distribute your y through, you'd get what we started with. That's a great way to test it. You can always test all of your answers in factoring. No one should hand in answers that are incorrect on mistake, because you can always check them. You already know what if your factoring is correct or not. Here's our second one. What do you see? What catches your attention? I notice that a 3 goes into all of these terms. I notice that I have an x in every one of these terms. So that means I'm going to pull out a 3x. What is that going to leave me inside? 3x times what makes 3x cubed? It has to be 3x squared. I took one of the x's away, so that left me with 2 more. 3 times 10 makes 30. I took one of the x's away, so that left me with just an x. And 3 times 25 makes 75. I took an x away. That leaves me with no more x's. So this is a GCF times a trinomial. Is this trinomial factorable? Not every trinomial is factorable, but is this trinomial factorable? Thinking about the same thing we did over here, what multiplies to be 25 and adds to be 10? X plus 5 and x plus 5. You could write it twice, but it's best if we write it as a square. That's a perfect square trinomial. That's fully factored. If you wanted to test it, you need to write this out twice, FOIL it together to make that, distribute it in to make that. You should be able to take your final answer and create the original question. What's different about letter C? What do you notice? Letter C only has 2 terms. So you should be having an opinion right now what you're going to do. I noticed that they both have a 5 and they both have g. So you take the lower exponent, which is g cubed. You always take the smallest exponent. Smallest exponent was to the first power. Smallest exponent was to the first power. In this case, the smallest exponent is to the third power. That's the least, or that's the most g's that you can take out of each of these. So that leaves me with 2 more g's here and no more g's there. 5 times 16 is 80. Now I'm looking at a binomial. This is the difference, and I recognize this is the difference of 2 squares. So if this is a difference of 2 squares, I can factor this one more time. This is 5g cubed. Difference of 2 squares would be g times g. That would multiply to be g squared. 4 times 4, that would multiply to be 16. And my signs would have to be different. This is the difference of 2 squares. These are conjugates of each other. If you FOIL this together, you get a 0 for the middle term. There's only 2 terms because the middle term is 0g. Negative 4g, positive 4g gives you 0g for the middle. That's fully factored. That brings us into the sum and difference of 2 cubes. Sum and difference of 2 cubes. There's a pattern we're going to need to use for this. It's a little crazy pattern. But once we work with it a few times, it's not too hard. But you got to do it a few times. When we're up here with the difference of 2 squares, we talk about taking the square root of the first term. And we take the square root of the second term. So we know what our numbers are we're going to work with. Well, that's the same idea that we're doing here, but we're going to take the cubed root. What times what makes a cubed? Well, a times a times a makes a cubed. And b times b times b makes b cubed. So we're going to say a plus b. Now, the common mistake is just to put a 3 up here in the corner. That is not what we're doing. That is not the same thing. you know that if there's a 3 up in the corner, that means you have to write the parentheses 3 different times and multiply it all out. And that gives you about a whole bunch of terms in the middle. This does not have any terms in the middle. So we need to multiply this to something that's going to create nothing in the middle. So here comes the crazy part. What's going to make a cubed? A times what? A times a makes a squared. A times a squared would make a cubed. So we totally understand why it's a squared. Because that's going to make a cubed. Now the weird part, this is where it gets a little strange, is just this middle section. We're going to use the opposite sign. We're going to multiply our two terms together, a times b. And then we're going to end it, always being positive, b times b. B times what makes b cubed? B times b squared. There it is. We can test this out. We can take a plus b and a squared minus ab plus b squared. We should be able to multiply this together to get what we started with. A times a squared is a cubed. Negative a squared times b. This is positive a squared. Whoop, sorry. We didn't do the last one. That is positive ab squared. So you take the a and you multiply it to each term. Then you take the b and you multiply it to each term. A squared b, that's a positive. That's a negative. A b squared. And then b cubed. So I have a negative a squared b, and I have a positive a squared b. I have a positive ab squared, and I have a negative ab squared. Oh my goodness, it worked. A cubed plus b cubed. That's my final product of multiplying these two together. That's why this pattern works. That creates the middle portion to cross out. And the same pattern is going to be true for a negative. A minus b, a squared, change the sign, ab, and then b squared. So what you're going to get here, a minus b, a squared plus ab plus b squared. This sign here is the same as the original question. It's the same as the original question. This one here is always opposite the original question, or opposite of this one. Same, opposite, and this one is always positive. And if you look at the beginning of each of those letters, S-O-A-P, you get soap. SOAP helps you remember what your signs are going to be for your perfect cubes. Sum and difference of two cubes. It's the same, it's opposite, it's always positive. Maybe that helps you. Let's go ahead and try this. First, we're going to think about what are perfect cubes. 1 times 1 times 1 is 1, of course. 2 times 2 times 2 is 8. So 8 is a perfect cube. The cube root of 8 is 2. 27 is a perfect cube. The cube root of 27 is 3. 64, 125. Those are some popular ones. 216. Later today we're going to use 343. 512 is 8 times 8 times 8. 729. And then of course 1000. Those are your very popular ones. Ones you could expect to see. So we'll come down here. We're going to factor this apart. Essentially, we're taking the cubed root of the first term. We're taking the cubed root of the second term. What times what times what makes that? That's what we did up here. What times what makes b cubed? B does. B times B times B. 3 times 3 times 3 makes 27. So what's my first term going to be? You take your A term and you square it. So you take this A term and you square it. You change the sign. You multiply the two together. And you square the second term. There you did it. It's as easy as that. Square it, multiply the two together, and square it. You can handle this pattern. Let's take a look here. What times what makes 27? So 3x times 3x times 3x makes 27x cubed. And 5 times 5 times 5 makes 125. So this is a tricky one. What's going to go in this spot right there? Everybody wants to tell me it's 3x squared goes here. What do you mean 3x squared?
9x squared.
Yeah, 3x squared means take your 3x and square it. 3x times 3x. Very important. Listen to that again. It's got to be 3 squared and x squared. You got to square 3x. That is 9x squared. 3 and 9 makes 27. Don't tell me it's 3. You got to be sure you write it as 9. You multiply the two together. And you square the b term. There you have it. This trinomial will never be factorable. You never have to worry about factoring this trinomial. Not in the sum or difference of two cubes. This is not factorable. If this had a 2 in the beginning of it, then it would be a perfect square trinomial. This is not a perfect square trinomial. All right. What do you notice here? Well, you can't take the square root of the cube root of 2. You can't take the cube root of 225. What might we do?
Divided by negative 2d squared.
We're going to factor out what's in common here. We're going to factor out a 2, and my lower exponent is d squared. So that's what I'm going to bring out. That's going to leave me d to the third power minus 125. 125 is a perfect cube. That I can work with. I can't work with 250. That's not a perfect cube. But 125 is a perfect cube. So what times what times what makes d cubed? What times what makes 125? Square my first term. Change the sign. Multiply the 2 together. And square your last term. That's the difference of 2 cubes. Notice that it is not parenthesis cubed. That's going to be the common mistake. That is not that. Here I notice they're both even. So I can pull out a 2 at least. I notice my lower exponent is 2, so I'm going to pull out b squared. That's going to leave me an 8. And yes, an 8 is a perfect cube. That's good. If I take 2 b's away from that, I'm going to have b cubed. Plus, take a 2 away from that, 343. Take 2 b's away, that leaves me with no b's. And 343 is a perfect cube. Perfect. I got the sum of 2 cubes. So 2b squared, what times what is going to make 8b cubed? 2b times 2b times 2b is going to make 8b cubed. And what times what makes 343? So it's a positive 7. It's the same sign as our problem. Then we square it. How do you square 2b? 2b times 2b. 2 and 2 is 4. b and b is b squared. Change the sign. Multiply the 2 together. And square your b term. There you did it. That was the sum of 2 cubes. This one had a GCF with it. When it has a GCF, it's a little tricky because you don't see it right away. So that's a new type of factoring pattern we have. Down here is not so new. Sometimes when you see a polynomial with 4 terms, 1, 2, 3, 4 terms, this is a cubic, would have 4 terms, you can factor it by grouping. Doesn't always work, but for some types of problems it works. So we know factor by grouping means we circle the first group, we circle the second group. So I would encourage you to physically circle those. Don't just use parentheses. Parentheses means something else in mathematics. Factor out what you can out of the first circle. Factor out the GCF of the first circle. What's the biggest number that goes into both of them? 9. H squared. So 9 times what makes 27? 9 times 3. Very good. H squared times h. I need an extra h to get h to the third power. 9 times 5, which h squared. That worked perfectly. Bring down your sign. That's why I don't circle it in that, is to help remind me that I'm going to bring that down. Now I look at 3 and 5. 3 and 5 has nothing that divides into both of them. So you have to at least pull out something. You got to have a place value holder. So pull out a 1. Negative 1 times 3h makes negative 3h. Negative 1 times a positive 5 makes negative 5. So notice how these two, what's inside the parentheses, these two parentheses are exactly the same. They have to be exactly the same, or else factor by grouping doesn't work. Perhaps you pulled out the wrong GCF. That happens a lot. You pull out the wrong GCF, they're not going to match. So that helps remind you to go back and look. But write down your 9h squared. Write down your negative 1. And then write down one of the parentheses. So we can factor difference of two squares, 3h minus 1, 3h plus 1, and then your final factor. So that is factor by grouping. This one looks a little easier because it doesn't have such big numbers in it. So reminder, we factor both groups. Pull out what you can. Bring down your sign. Factor out what you can. 16 times y makes 16y. 16 times 3 makes 48. Our parentheses are exactly the same. And we get y squared plus 16 and y minus 3. Now, many people think that we can factor the sum of two squares. You cannot factor the sum of two squares. This was the difference of two squares, so your signs could be opposites of each other. You could use conjugates to get 0 in the middle. You can't do anything with a positive 16. Because if you used y plus 4 and y plus 4, that would give you 8 in the middle. So you cannot factor the sum of two squares. You can work with the sum and difference of two cubes, but you cannot work the sum and difference of two squares. Only the difference can be factored, not the sum. Right, the last example that we have, it looks really intimidating, but it's the same patterns that we have used before. In our previous lessons, we've always worked with x squareds. So we had x and x to make x squared, and then we had some number. So if we have x to the 4th power, all we're going to do that's different is use x squared and x squared. That's going to multiply together when we FOIL it to become x to the 4th power. Similarly, if we have x to the 6th power, we're just going to use x to the third and x to the third. That's going to multiply to be x to the sixth power. So we don't have special rules for multiplying to the 12th or the 4th power. We're going to use all the common rules that we've already learned. So first thing we look at is, do we have a GCF? So that leaves us with m to the 10th power plus 18m to the 5th power plus 17. Notice how this is 10 and this is 5. This term is half. The exponent is half. This is a pattern of a quadratic. So what that means is that we can write this down as m to the 5th, because when we multiply there, we get m to the 10th. 17 and 1 is what multiplies to be 17. And they're both positive because they add to be 18. There we factored it apart. This one down here, this looks like the difference, but this is the 4th power. We don't have a rule for the 4th power. We're going to treat this just like a quadratic. Can you take the square root? So you get 4g squared minus 25, 4g squared plus 25. And then you have again the difference of two squares. But on this side, we do not have the difference of two squares, so you cannot factor that. Then for the last one, we have a GCF. And we're going to treat this one as a perfect square trinomial. I'm sorry, the difference of two squares. Again, the difference of two squares. But this is the sum of two squares. You cannot factor that. So now it's fully factored.